Okay, off we go. So, two quick observations. First of all, don't forget about the attendance quiz. Attendance code, here it is. Make sure you get this in. Make sure you confirm you get the credit. Make sure you see, correct or 1 out of 1, or make sure you see that you got the credit for it. Second of all, full props to Duke Maintenance, Duke Facilities. They got the AC fixed. It's much more comfortable in here than it was Friday, so that's lovely. Okay, so here's about where we were last time. Well, let me rewind just a little bit. We'd introduced this idea of intermediate variables. In particular, if you take the matrix form of the chain rule and say, hey, you know what though? I'm really only interested in this one single partial derivative. How would I compute that one single partial? Well, yeah, you do that. This is how matrix multiplication works, right? You corresponding row, corresponding column, you dot them. There's the formula. And then we spent a little bit of time talking about the very dangerous, what the unfortunate notation kind of suggests. This looks like something where you can cross them out, but you can't. Those are not the same thing. The notation, it is what it is, and I don't have a better idea. And heads up, right? Don't make that mistake and write down nonsense. If you were to write this down by itself, it's just purely wrong, and furthermore, again, it kind of betrays a fundamental misunderstanding of what's going on. Okay, so careful with that. Moving along, how do we think about this equation? Well, not losing sight about the fact that it comes from the matrix form. It's just a narrow sort of part of the matrix form. There is another nice way to think about it. So, in particular, you can kind of see the composition. This is the first function, and then this is sort of the second function. Right? We know we're interested in how this variable changes per unit change in that variable, and it's a partial derivative, so we know that these variables here aren't allowed to change. Right? Only xj in that, in sort of the left column there. So what happens, and let's just kind of think it through. If you change xj, y1 depends on xj. And as you change xj, that's going to cause y1 to change. It's also going to cause y2 to change. It's also going to yada, yada, yada. All the y's are going to change as a result of little changes you make to xj. And here's the thing with that. Every one of these y's that changes is going to contribute in its own little way to how much zi changes. So, to some extent, changes in xj, I like to say, propagate along this, let me do it like this, propagate along this path through y1 to cause a change in zi, but that's just not the only propagation path that we have to deal with. Changes in xj also contribute changes to y2 that will contribute to changes in zi, etc. So we kind of have to we have to account for all of these different paths. Let's take them one at a time. Let's start by looking at this path here. And let's ask the question, okay, per unit change in xj, how much does y1 change? That's what this partial derivative is. Okay, well, yeah, okay, sure. Well, that tells you how much y1 changes. But wait a second now. Per unit change in y1, how much does that contribute to the change in zi? Well, that's what this factor is. Right, so multiplying these two partials together kind of accounts for, as xj changes, those changes are going to get, in some sense, magnified by this red partial, that factor right there. And then, however much that's magnified, it's going to be further magnified by, this dark blue partial. So, altogether then, each path gives you a term in your chain rule. What do you think? Everybody kind of buy it? Okay. All right, now I will further make the observation. Every term corresponds to a path, but notice every path also corresponds to a variable, and it's a variable at this intermediate stage, right? It's not the sort of the original domain, and it's not the eventual target. It's that one kind of in the middle. So we call those intermediate variables, and conveniently, terms correspond to paths. Paths correspond to intermediate variables. So you can think of it as you get a term corresponding to every intermediate variable, and the structure of those terms is always the same. It's very handy how consistent this is. The intermediate variable itself will always go there and there. It'll always be that temptation to cancel, which you can't do, right? The partial zi will always be there, and the xj will always be there. All the terms structurally will look just alike, and you just get a different one for each intermediate variable. So, for example, this intermediate variable gives you this term, which you'll notice has the same structure, right? There's the intermediate variable. There's the output variable we're interested in. Here's the input variable we're taking the partial with respect to. Same exact structure. So I think it's a great way to think about it. And there are a lot of situations where you might not need the entire derivative matrix. You might actually only be interested in one individual partial. And when that's the case, I think this point of view of intermediate variables leading to an equation like this, quite a bit more convenient than writing out the whole derivative matrix and computing a bunch of stuff you don't actually care about. Okay. All right. So let's do one. Here's a couple of functions. Now I'm going to notice that it's been set up in a way that's very convenient, that what comes out of the first function is what goes in to the second function. So it's been set up very conveniently for composing. And let's see here. We are going to be interested in computing. Whoops. Come on. Okay, my thing is. Okay. I don't know why this thing dies so fast. We're going to be interested in computing the partial of Z2 with respect to X2. Right? Input variable, output variable. How are we going to compute that partial derivative? By the way, one thing I suppose, if what you were interested in is the answer only, which by the way is not us, right? We're interested in reasoning, not results. I suppose one thing you could do is you could take these explicit formulas for y1 and y2 and plug them in and get a great big gigantic expression that explicitly gives z2 as a function of x1, x2, x3, and then basically do a partial derivative. That's not what we're going to do. By the way, be aware on a test question, part of your responsibility for as a student taking a test is to interpret the question appropriately. So a question like this, the obvious intention of the question is for the student to demonstrate proficiency with the multivariable chain rule, right? So if you plug it in and bypass the multivariable chain rule, that's a pretty obvious sort of missing of the point of the question. Does that make sense? I hope that makes sense. So just keep in mind, it's not going to be graded on the basis of whether you get the right answer, right? So the fact that there's another way to get the right answer is just not relevant, right? It's going to be graded on the basis of did you demonstrate the proficiencies that we're interested in. Anyway. Okay, so how to do this? I am a big believer in the idea of always having a good diagram. I cannot emphasize this enough. I think it's indispensable. This first function, the x's are the inputs, the y's are the outputs, right? So this first function right here, draw that first. And then Let's see here. Those outputs from the first function are the inputs to the second function, whose outputs are then these. And so this second function shows up like this. Right, and all together then, now I have a single diagram that sort of keeps track of everything. All of what I was given, this is what keeps track of what depends on what. This is what's going to allow us to see which variables are playing what role at what stage of the calculation. It's just really, really handy. Okay. All right, so keeping that in mind, then let's get to answering the question. We're looking for a partial of Z2. Well, there it is. We're interested in the partial of Z2 with respect to X2. There it is. And the diagram is now doing us a couple of really nice favors. One is, well, I can see that X1 and X3 are constants. I'm taking a partial with respect to X2. X1 and X3 are the other variables in its world. They are therefore held constant. Oh, thank you, diagram. That's really nice. The other thing you can see here is I can see exactly what my intermediate variables here are. Like along what paths from X2 to Z2 can changes propagate? Well, they're going to have to go through one or the other of these variables. So keeping in mind intermediate variables. Oh, hang on a second. Erase. Do it like this. Intermediate variables correspond to paths. Paths correspond to terms. And so I have a y1 term and a y2 term. And notice z2, x2, right? And then the intermediate variables show up following the same pattern in both terms. Everybody good? Here, by the way, here's a common mistake that I see, periodically. Students who don't, draw a diagram and let the diagram be their guide and, do what the diagram instructs you to do, basically, is I'll see extra terms. I'll see another term here, like a Z1 term. Well, it doesn't make any sense. Z1's not an intermediate variable. It's obviously not an intermediate variable if you're looking at the diagram, right? But if you don't have a diagram, you're just like, I guess I need to consider all paths, and Z1's a variable, and you can see how without a diagram, someone might be tempted to think that is an appropriate term to write down. And likewise, maybe a Z3 term or something like that. And that's just doesn't make any sense. Okay, and then it's all details from here. We have explicit formulas for these functions, right? For example, I know that Z2 is that function right there. And so what is the partial of Z2 with respect to Y1? Well, easy partial, and it's that right there. Likewise for the others. Everybody happy? Yes?
How do you determine that X2 comes from Y1 and Y2?
So there's a lot of arrows on here that I didn't draw. In some sense, when when you have something like this where the y's are functions of x1, x2, x3. It says right here y1 and y2 are functions of, and what the actual functions are isn't the point. The point is these are the outputs, and x1, x2, x3 are the inputs. In some sense, all of these arrows are all there. I just didn't want the picture to get all muddled, right? So what I knew from the question itself, I knew I was going to be interested in starting at x2 and going to z2, and therefore, from x2, the fact that x1 influences y2 has just got nothing to do with what x2 is doing. Does that make sense? Yeah. So really, this is these just happen to be the only arrows that could matter. Yeah. Okay. All right. Okay, moving along. Real easy to mess this up. Now, this is a single variable calculus thing. I'd like to start with single variable examples so you can kind of get the idea of what we're talking about, and then we'll just say, well, there's a multivariable equivalent. And I do this a lot. I've already done this several times, and I'm going to keep doing it throughout the course. But here's an easy question that y'all would all recognize. Here's a couple of single variable functions. We're allowed to compose functions, and we're allowed to ask what the derivative is. And here's two different calculations. I'm not going to go through the details of the calculations because it's hopefully clear what went wrong in the first calculation and what was better in the second calculation. In particular, when you do a derivative of a composition, you got to remember that the second function's derivative is evaluated not at x, but at f of x, right? So again, flashbacks to Calc 1. Okay. And that's what I did wrong previously, in the wrong calculation. You see where an x squared should have been, I didn't plug in the x squared. Okay. All right. Now I propose, though, that both of these calculations are suboptimal. Even the one that's valid, I think, is pretty suboptimal. Let me explain why I don't like about it. I don't like the fact that I claim even this kind of sort of commits a confusion of variables. And let me represent this with a diagram. We know we're composing, right? We've got this function f that's acting. And then after f, we're doing this function called g. And okay, well, f is going to have some sort of an input variable, and f is going to have some sort of an output variable, which is going to be the input variable for g, which will then have its own output variable. And I propose, I claim this is pretty clear, that these three variables, the original input, the eventual output, and the intermediate one, they're all different. Modest proposal, when three things are different, they should have three different names, right? You shouldn't use the same name to refer to different things. Okay, well, okay, fine, but here's what follows from that. Whatever comes out of f can't be called x. I can't have x being both the input and the output from f. That's insane. They're different things. You can't give the same name to different things. But whatever comes out of f also has to be what goes in to g. So the thing that goes into g, the variable that's the input for g, what g is written in terms of, should not be x, right? And both of these solutions I had previously, let me do like this, try to get this, there we go. Both of these solutions up here, they wrote g in terms of x, which doesn't make any sense, right? You draw a diagram, you think about the roles that the variables are playing, you can't write g as a function of x. G has to be written in terms of, well, I think it would make sense to call it y. Right, so notice what I've done is I've just rewritten here. Same exact function. This is, the function that cubes whatever you give me. Same exact function down here. The function that cubes whatever you give me. I just wrote it with a different dummy variable y instead of the original dummy variable x. And I claim you should do that every time. Right? It's an outrage to try to do business where you've got x doing two different things in two different parts of the calculation. It's literally confusing. Does that make sense to everybody? So it's an easy fix, conveniently. All you got to do is take your second function and just rewrite it in terms of a different dummy variable. All right, and having done that, look how easy the calculation becomes. the same calculation, but let's see here. The derivative of f, you write down. The derivative of g, you just write it down. Don't worry about, oh, wait a minute, where do I evaluate it? I've got different names for the different variables. Where do you evaluate g prime? Well, at y. It's written in terms of y, so you evaluate it at y. Nothing to keep track of, nothing to remember. And then at the end, then at the end, you recognize that the composition is a function of x. The derivative should therefore be written entirely in terms of x. That's your prompt that I should figure out how to get rid of this y. How am I going to get rid of y? The thing that went into g, oh, well, it's the output from f. And so that y is x squared. And then you plug in and do the algebra and boom, victory. So, short version, don't confuse your variables and everything goes through very conveniently, right? Big point, don't confuse your variables. Okay, now that's single variable calculus. What a waste. Well, the point here is that the exact same issues come up in a multivariable setting, and it's really easy to mess this up. I see this all the time, that students are so distracted, very reasonably, by, oh, wait a second, how do I write down a derivative matrix, and which order do these matrices go in, and which one's first and which one's second, and keeping track of stuff like that, and forget to think about, wait a second, where do I plug in, and stuff like that. So the solution as I see it, always watch out for a confusion of variables and fix if need be. So, two functions, nothing wrong with either of those functions, perfectly fine. Not a thing wrong with that. But as soon as I say I want to compose them, as soon as I recognize that what comes out of f needs to go into g, well, okay, whatever comes out of f, I can't call it x and y. I'm going to have to call them something different. Let's try u and v, whatever. Right? And that means that what goes into g needs to be those same variables u and v, which means that I need to rewrite now. Got to rewrite this function g, same function, just rewrite it in terms of the newly identified different dummy variables u and v. Notice nothing happened. It's the exact same function, right? Just different dummy variables. Now we have fixed our confusion of variables. Right? Forget about all of this. We're not using that anymore. We're using these formulas for f and g. Confusion of variables gone. Go about your business. Don't worry about it. Everything's going to work out in the end. And let's play that out. Let's see that happen. So let's see here. Yeah, you take the derivative matrix for f. Right, various partials. Y'all remember how to do a derivative matrix. Go ahead and take the derivative matrix for g. Again, various partials, compute as you must, and you end up with this. And then you multiply per the chain rule. Make sure to get the order right. F acts first, which is on the left in the diagram. It's on the right in the algebra, and that makes it the right matrix. Let's see here. Let me do, come on. The right matrix. And then G is second. It's on the right in the diagram. It's on the left in the composition. It's the left matrix, and so that goes there. You multiply the matrices, and it's basically all over. And then again, you just have to recognize, well, we got to rewrite everything in terms of x and y. The composition, after all, the composition, after all, is a function of x and y. if I need everything written in terms of x and y, what am I going to do about this u right there? What was the deal with u? Oh yeah, u was our first input to G, which means it's our first output from F, which means it's x squared plus y squared. And you plug that on in. And again, notice the diagram. Well, the diagram's doing so much for us, right? It's keeping track of what variables are playing what roles and what relates to what way. Make sure to have a clear diagram and give yourself those advantages, right? Don't try to do it with one hand tied behind your back. The diagram is so helpful and convenient. Okay. All right. Okay, so this is, again, warning, be careful, don't confuse your variables. I claim this is actually a special case of a larger problem. The larger problem, let me make sure my thing is, yeah, it's working again. Okay, so the larger problem, we have to recognize our chain rule only applies to compositions of multivariable functions. And let's see here. I think I can hit the, let's see how it, Alt-Tab. Yeah, okay. So flashback to last time. This is our multivariable chain rule. You can view it as, the factor that you multiply by x prime to get y prime, and the factor you multiply by y prime to get z prime. Those factors multiply to give you the overall factor, and that's all the chain rule says. Right? We talked about that at length last time. So here's our multivariable chain rule. But very importantly, we are, strictly speaking, composing these two functions, meaning that what comes out of the first function is exactly what goes into the second function. This is a very specific structure of, we could write it in terms of variables and things, but it's a very specific structure of what we're dealing with. So, yes, it is true that when you have a composition of functions, you can write a corresponding diagram. I'm a big fan. It is not true that every diagram represents a composition of functions. So here's a nice example of a diagram which does not represent a composition of functions in the sense that I just described previously. There's a list of requirements here, right? But are there functions f and g with unambiguously and uniquely named inputs and outputs such that the outputs from the second one are the inputs from the first one that produce a diagram exactly like this? No, you can't do it. So it's tempting to think, okay, we've got a way for writing down the chain rule. You just kind of look at the diagram and draw lines and stuff. We don't have that. Our chain rule only applies to compositions of functions. Now, situations like this one here do arise, and we're going to do an example, specific example here. If you look at all these formulas down here for y1, y2, z1, z2, you connect the arrows for which ones are specifically listed in the formulas, you'll get this. And you might want to take a partial derivative. Maybe you want to compute the partial of z1 with respect to x1, but as of the moment, I'm not even clear what that means. Let's just think it through. What does partial of z1 with respect to x1 mean here? Okay, well, z1 seems to depend on these three variables. So maybe partial of... oh, come on, already? Okay, sorry. Maybe partial of z1 with respect to x1 means that I hold these two variables constant and then take the derivative of green with respect to blue. That's what we've done in the past with partial derivatives. I claim that's a bunch of nonsense. What do you mean you're going to let x1 be a variable, but y1, which depends on it, is a constant. You can't do that. If x1 changes, y1's gonna change. You can't just say it's going to be a constant, right? You ever see the problem of that? So I don't know what this means based on what's written here. And that's not good, right? You can't do math writing down a bunch of stuff you don't even know what it means, right? That's no good. So there are different ways that you can treat this. I'm going to show you what I consider to be a natural, perfectly well-ordered and organized means of turning this confusion into a problem for which we have a method which we can just do and everything lays out and it's fine. That's not how most people in practice do it. Most people in practice write down a bunch of stuff that they know what they mean as they write it, but a reader who is new to the ideas, as y'all are, won't know what they're talking about. Okay, so I'm going to show you what I consider to be the easy tweak that will turn it into a problem that we can totally do, and then I'll talk through in practice how you would actually put this into practice in real life. Okay, all right. So what I'm going to suggest is that we introduce a new variable. I'm going to introduce a new variable right there. That new variable, I'm going to call it x1 star. It is just a copy of x1. That's all it is. It's a copy of x1. The formula for this new variable, this new x1 star, the formula is just x1. It's literally x1. So I haven't really done anything. Right? But now I can rewrite z1. Instead of viewing Z1 as a composition where, oh my gosh, I don't know, what is that? What's constant? What's a variable? Can you do that? Does that even make sense? Right? No such issues. Right? Because I'm going to rewrite Z1 now as a function of those variables. Now, it's a little bit concerning. It's like, well, wait a minute. Everywhere I see an x1, I'm going to put an x1 star. That's a different variable. But wait a minute. That new variable, x1 star, is x1. So nothing happens, really. This is perfectly legal. I'm just, again, going to replace the x1 with x1 star. Okay. So my diagram, just so we can move down to have it all on one screen here. My diagram changes. Here's my new intermediate variable, x1 star. Again, it's just x1. Now notice I do have a composition. There is a sort of a first function. Let's call it f. There is a what you might call a second function that we can call g. The intermediate variables make sense. What comes out of f is exactly what goes into g. Those intermediate variables are all independent of each other. It's all good, right? And we've got a chain rule for when you have a composition of functions like this. We can just write down the chain rule, and the thing that we're interested in, reminder, interested in partial of z1 with respect to x1. Okie dokie. Well, z1 is there, and x1 is there, and I have three paths that therefore give me three terms, and everything's fine and answered. No problem. And now I will point out that this expression right here, partial of x1 star with respect to x1, well, that's a freebie. x1 star is x1. That's kind of the whole point here, is that, I don't actually want to change the question. So x1 star is x1. So that partial derivative is just 1. And so that factor just disappears. That's very convenient. Okay. All right. Now, here's the bad news. What people will actually write down, most of the time, in my experience that I've seen, instead of writing this down, most of the time they won't actually do that. They won't make the new diagram, right? They'll just write this. I mean, they've got that in their head. They know what they're doing. I'm not accusing any, working mathematicians, physicists of not knowing what they're doing. Of course they know what they're doing, right? But it's in their head, and they knew what they meant when they wrote it, but since they didn't create a new variable, they write it down like this, and it's super awkward, I think, that they're saying the partial of z1 with respect to x1 is a certain formula involving the partial of z1 with respect to x1. It makes it look like they're answering a question in terms of itself, but these are different. But they'll write them the same. I find that mind-bogglingly confusing. You know what I mean? So I find that very unsatisfying. Look how easy it is, though, to tell the difference between these two things if we do keep them separate, right? If we make this distinction, introduce this new variable. Partial of z1 with respect to x1 star is just that right there. And the partial of z1 with respect to x1 is sort of, we have all three of these terms. It's the overall, for the overall contribution from all three of those paths. So these are clearly different things. They don't even look the same in the diagram. They have different notations. Very important. Everything sort of makes sense. So anyway, I encourage that you do things this way, and then, obviously, you can take all of these partials you can compute from the equations we have up here, and go proceed along and get your answer. I strongly encourage doing things this way. Be advised, though, that in practice, in physics books that I've seen, they don't expand this out. Okay. All right. Okay, second derivatives. I think the best way to understand how to do second derivatives is just dive in and see an example. So I'm just going to do that. I'm going to dive in and start with an example. Just a little bit of a preview. We will at some point make big use out of this observation. It's not a deep observation, but it's extremely helpful at a key stage. If you have z, that's a function of x and y, its partials also functions of x and y. So make this quick observation. All right, and let's see here. I'm going to, if y'all will bear with me, I'm going to scratch this off for a quick moment. Just for dramatic purposes, we'll reveal that in a second, but let's pretend we haven't seen that. Okay, here's the question. If z is a function of x and y, and if r and theta are polar coordinates, keep in mind polar coordinates give x and y as functions of r and theta. Right? Remember those formulas? X is r cosine theta, y is r sine theta. So we have a composition here, and let's suppose that we want to compute the second partial of z with respect to r. How are we going to do that? Hopefully no surprise, we're going to take an r partial, and then we're going to take an r partial of that. So that part of the problem is straightforward. The first partial of z with respect to r, two paths, two terms, no big deal. Chain rule, right? That's our regular old chain rule. Let's see here. We can simplify a little bit there. After all, we know polar coordinates, and so these two partials are easy. I mean, don't forget. For example, y, that's r sine theta. So the r partial of that is just the sine theta. Okay. And then I'm going to rewrite just for sort of compactness, kind of lays out a little bit better on the page. You'll see that as we develop the calculation. I'm going to choose the subscript notation for this partial derivative instead of this kind of fraction-like notation. Okay, now we're going to take that R partial, and we're going to take, as promised, the R partial of that R partial. Everybody with me? Okay. So let's see here. By the way, notice we're taking a partial with respect to R. That means theta is a constant. Nice little reminder from the diagram. Again, I'm a big fan, right? Please draw your diagrams. It's just helpful in any number of different ways. So if theta is a constant, then that means cosine theta is a constant, and then sine theta is a constant, and those constants factor out. Isn't that nice? Cool. By the way, if that hadn't been, we got lucky on that one. It happened to be that we've got these two factors in each term, and it happens to be that one of them was a constant. If it hadn't been, which it won't always be, and by the way, there's a homework exercise where it won't be, then you have a product of two things, neither of which is a constant, and again, no big deal. Well, then product rule. Will you take a derivative of a product? Use the product rule. So anyway, we're lucky on this one that we don't have to, but using the product rule is something y'all are familiar with. Okay. Now, we find ourselves looking at this. Partial of zx with respect to r. Let's look at our diagram up here. I don't see zx. Okay, you'd be tempted to look at this thing, and I'm going to put a question mark here. We're thinking about it. It'd be tempting to call that z x r. Because we're starting with z, then it says we're taking a partial with respect to x, and then it says we're taking the partial with respect to r. And I claim you can't do that. That doesn't make any sense. It's nonsense. And the reason that's nonsense, look at our diagram. This would suggest that z is a function of a collection of variables including both x and r. In other words, it kind of suggests we're viewing z as a function of all of those. And again, I claim that doesn't make any sense. I mean, okay, for example, if I was going to take a partial of z with respect to x, are we saying that I'm going to let x be a variable? Oh, now this thing has died. Oh my gosh, my styluses are just working against me here. Maybe this one will be back in business. Yep, okay. Okay, so partial with respect to x would suggest that I'm going to have x be a variable, but these other variables all be constant. Well, that's nonsense. You can't change x while holding r and theta constant. If r and theta are constant, then x has to be a constant. Right? So it doesn't make any sense. This is, you can't do that. Right? Is that cool? Does everybody see the problem? It just doesn't work. So what are we going to do? What does this mean? And here's where we have the big reveal, why we care about this observation. If z is a function of x and y, just remember, zx and zy are also functions of x and y. So indicate thusly on your diagram. Zx and zy are literally functions of x and y. That's all I'm saying by adding them to this diagram like so. And in doing so, now I can make perfect sense out of this partial derivative. You want to take the partial of zx, oh, there it is, with respect to r, oh, okay, well, there it is. No problem. Two paths, two intermediate variables, and that partial derivative then has two corresponding terms. It turns just into another chain rule situation. So, again, the thing that makes this possible is actually indicating on your diagram that you're recognizing that zx is a function of x and y, and then, again, it just leaps off the page at you. Well, we have two intermediate variables, and boom, 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 nothing to it. How we doing? Everybody all right? Okay, so likewise for the other terms, everything else is details at this point. That's the key ideas. I want to encourage you all to think through the rest of the calculations here. In particular, what are you going to do about that? Think through how that turns into this, and then et cetera, et cetera. Okay, now why this is important. By the way, the book doesn't have much discussion, if any, on this, if I remember correctly. I think it's a real gap, a real problem. There are lots of situations that come up in what I'm going to call real life as an engineer or physicist or a mathematician, where you really need to be able to talk about second derivatives with the chain rule. Really important. And a great example is the Laplacian operator that has this formula, comes up in very natural ways for what I'm going to call big physics concepts. How heat flows is a big deal. It's in everything, right? How electrons behave governs how circuits work, and how quantum mechanics, in some sense, is about how electrons behave in an atom or a molecule, something like that. I mean, it's just immensely huge ideas, and this formula that I have here, it turns out you can write this using second derivative chain rule, not unlike what we just did, in spherical coordinates. So this is what we call the spherical Laplacian, and if you we did a polar second derivative. This would be a little bit different for it to be spherical, and the algebra does get quite inconvenient. I'm not recommending that you should do that, but I claim that if you go through the whole process, this is what the spherical Laplacian looks like. And again, that is an immediate consequence of this kind of a calculation, but spherical instead of polar, and more details. Okay, so here's kind of a broad brushstroke. Here's kind of a polar equivalent. Polar partials, you can write in terms of rectangular partials. This is what we did on the previous page. And then you can just solve for the x partial and the y partial like that. This is easy algebra to do. Make sure you can do this, right? So just solving literally for the part d by dx and d by dy, you'll get these expressions. And doing a spherical equivalent to that will allow you to solve for this rectangular second partial in terms of spherical second partials. Okay, who cares? Here is a very common calculation that y'all are going to probably have to do at some point. If you ever study electric potentials, right? Again, mostly engineers, you're going to be studying electric potentials, right? Well, electric potentials have to satisfy, under certain appropriate conditions, have to satisfy this equation. That is the Laplacian from the previous page, which again, you could do it in either rectangular or spherical. What turns out to be a valid solution, this right here, well, appropriately, you can write as either that or that. But if you want to make the assertion that this actually works, you have to actually compute that and confirm that you actually get 0. So what we have to decide now is, do we which of these calculations would we rather do? I think you can probably tell this first calculation is going to get a little hairy because there's fractions and there's square roots and there's a composition in the denominator and there's second derivatives, and it's going to get hairy. By the way, everybody should do that once in their lives. I did mine's your turn. Give it a try. It'll take you probably 15 minutes. I don't know, 10 minutes, something like that. But everyone should do that once in their lives. It's pretty inconvenient, but anyway. But here's the much better one. Much better. Oh my gosh, so much better. Let's look at the spherical one, which looks like a nightmare. Look how easy this is going to be, though. The very first thing that I need to do here is I need to take a theta partial of that expression, which doesn't have any thetas in it, 0. This whole term just disappeared. No square roots, no quotient rule, no composition, just 0 instantly. Let's look at the second one. The first thing I'll have to do in the second term there is take a phi partial of that. Oh, well, there's no phis in here either. 0. Instantaneously, right? No effort. So not only does that immediately disappear, but that immediately disappears. And then the only sort of non-zero, the only non-trivial work I have to do is I am going to have to take a rho partial. This does obviously have rows in it, but it's an easy derivative. The derivative of k over rho with respect to rho, negative k over rho squared, which I then multiply by rho squared, which makes this a constant, and any derivative of a constant is 0. And so that disappears as well, and we win. Right? So it's a super easy calculation. This calculation, it looks a lot worse. It looks like it's going to be a nightmare, but it's worlds easier than what looked like it would be the winning bet. So anyway, big fan, and the credit goes to these ideas here of how to take second derivatives in the chain rule. Y'all have a good week. Y'all have a good rest of your Monday. See you Wednesday. Sorry, it feels like a week's past already.
Thank you.
Yeah. See you later. Okay.